Hello, I'm Grylls, and I take on the most challenging environments to teach you how to survive. This is Man vs. Wild. Welcome to Man vs. Wild. I'm Grylls, and today we're going to be talking about what happens when you're in the wild and there's nothing but water and sunlight and you have no food to nourish yourself. Well, that's where we use photosynthesis. I'm joined today by my friend Chlorinance the Chloroplast, who will be able to help me to explain this strange phenomenon. Hello, Chlorinance.
Hey Bear, how's it going?
It's going well, thank you.
I'm just gonna perform some photosynthesis today.
Fantastic.
Great. Okay, first, I receive sunlight through and into my pigments, and there, the sunlight energy is stored.
Wow.
I also have two electrons, can you see them? Right here, in my chlorophyll reactive center. This chlorophyll reactive center operates at about a wavelength of 680. And see, once that light energy is captured, it's converted and stored and excites these electrons, see? And then once these electrons, they shoot up through and are captured by the electron transport chain.
Fantastic. The question is, what happens to the electrons? How do we replace them in the chlorophyll reactive centers?
So then, to replace my electrons, I take a water molecule. Do you see right here?
Water molecule.
And then I break it apart into two protons, which are also known as hydrogen ions. And I leave them in my thylakoid space, can you see?
Fantastic.
See, and then there's also one oxygen molecule left over.
Right.
And then, two electrons are taken from that breakdown, and those replace electrons that were lost.
Fantastic.
So now, the two electrons, once they pass through, they lose a little bit of energy, and the energy stays there, and it drives the active transport of the ETC. And that creates a proton gradient. And that proton gradient allows these hydrogen plus ions to travel through the ETC and join the rest in the thylakoid space. ATP synthase helps me transform the energy from the proton gradient into chemical energy that we use to create ATP. And the way it does that is that ATP synthase has a channel that allows hydrogen plus ions from the thylakoid space to travel back up through it into the stroma. ATP synthase then uses that energy to make ATP. It does this by adding a phosphate to an ADP.
Fantastic.
We're at the very end of our adventure in the process of photosynthesis. Now I will take you through the path of photosystem 1, which operates very similarly to photosystem 2.
Why did photosystem 2 become before photosystem 1? Because scientists are idiots and haven't lived in the wild.
Anyway, sunlight, much like photosystem 2, hits the pigments and charges the two electrons in my reactive chlorophyll, which operates at about 700 wavelength. And once these electrons receive that energy from the sunlight, they travel through to the ETC of photosystem 1. And once they travel through, they do not operate in the same way as the other ETC, but however, they react with a thing called, as you can see here, NADPH+.
NADP plus.
And once these two come in contact with another, this becomes NADP minus. And because of the excess hydrogen plus ions, it then becomes NADPH.
Because the 1 minus balances out with the 1 plus and joins together to become a neutral molecule. Fantastic. Thank you very much, Chlorinance. We appreciate your help. Alright, well now, I'm gonna go off, have more adventures, and drink more of my own urine. But until next time, goodbye.
Great.
It's a bird. Wow.
Now then, I create ATP. So, excuse me. Wait, no.
Never mind. This is a bay tree. This looks absolutely delicious. Ah.
Damn. Shit. Photosystem 2. Oh shoot, no yes. I take a water molecule. Do you see right here?
Water
And then I
molecule.
break it apart into
Wow.
two proteins.
And there's a gradient. It's a preparation for a lot of energy.